Alright, okay, so let's recap on the chapter of the transfer of thermal energy. And the first LO that we need to know is to actually show understanding that thermal energy is transferred from a region of higher temperature to a region of lower temperature. Okay, so what this means is, for example, if I have a hot object of 70 degrees Celsius and I put into a water of 40 degrees Celsius, there will be a net transfer of thermal energy into the water of lower temperature. So energy will be going out. Thermal energy will be transferring to 40 degrees Celsius. And you will continue until this thing is achieved. This thing called thermal equilibrium. So what this means is it is the same temperature. So this will continue to transfer energy out and it will continue to cool down, while this will gain thermal energy and heat up. Eventually both will reach the same temperature, and net transfer stops. What's important to know over here is it's a net transfer. Energy is still being transferred between the two objects, just that overall no one is gaining and no one is losing. So what common question can normally come from this? They might ask you, what is the final state? Will the temperature be different or not? They might also ask you, whether energy transfer from a region of higher temperature to lower temperature or the other way around. Let's take a look at the second LO. Describe in molecular terms how energy is transferred in solid. So what this is basically asking is, how does conduction works? So conduction, there are two main parts, one for non-matter, one for matter. Because of the word describe, you need to know the way to describe how conduction works. So what are the main points over here? Main point number one, the particles at the hot end will vibrate more vigorously as they gain thermal energy. They will then collide with the neighboring particles, causing them to vibrate more vigorously. And this actually transfer thermal energy to the cooler end. So if you look over here, the heat supply is here, and as they gain energy, they actually vibrate more, and they actually collide with one another, passing down the energy, causing the neighboring particles to vibrate more vigorously, and eventually, the one at the end will vibrate very vigorously as well. That's for non-matter. Then we also need to know for matter. So in addition to all these, matter also have this thing called the free electron diffusion. As name suggests, free electron means they can move about. So when it is heated at the end, they will absorb thermal energy and gain kinetic energy. These will then move towards the cooler region at high speed, colliding with the particles over there and make them vibrate more vigorously. This causes the energy to transfer to the cooler end. So going back to our diagram, so as the electrons are heated up, they actually try and move towards the end. Of course, some of them won't make it. But you can see overall, there's a net movement towards the cooler side, causing the particles at the cooler side to actually heat up. Besides knowing how to describe, what else is important in this part of the chapter? You should understand the rate of conduction. So what do I mean by that? For solid matter, conduction occurs faster than solid non-matter, because matter has free electron diffusion. And solid, the particles are closer together, as compared to liquids, which are further apart. This means that the solid particles can collide with one another at a faster rate because they are very close together. That's why the conduction is faster for solid, then liquid, then gas. Of course, after conduction, we have our convection. So describe in terms of density changes, how convection occurs in fluids. So what is important over here, again, you need to know how to describe the process. So this is how it works. The liquid, at the bottom, gain thermal energy and expands. So when I supply energy, okay, the liquid over here actually expands. Okay, this reduces its density, causing it to rise. Okay, so my hotter water, okay, that's less dense will rise, and this causes the surrounding cooler and denser water to sink to the bottom. Okay, the process repeats to create convection current. Okay, note that this last statement is very important as well. Okay, do remember to write it in your answer. Okay, so what are some other common questions? Okay, they may ask you, okay, whether the convection is effective or not. Okay, so what I mean by effective, okay, what I mean is, okay, can very nice convection current be formed, or okay, will heating or cooling occur very quickly or not? Okay, so for the first one, okay, is effective, okay, because okay, your hot water actually rises due to expansion, so the water over here can rise. Okay, water over here can rise. Okay, while the cooler water can sink in from this side. Okay, but if you look at the not effective one, okay, the heat is actually at the top. Okay, so what this means is, okay, the hot water will try and rise, okay, and perhaps the cool water from the side will try and go in from the side. Okay, and you realize that, okay, the other parts of the water, okay, not much convection current is being formed. Okay, the hot water, because being less dense, it will rise, okay, and it won't sink. Okay, so all these waters, okay, are actually getting heated up by conduction only. Of course, besides heating, okay, we also have cooling, okay, your aircon over here. Okay, so as the air is cooled, okay, the cold air actually sinks to the bottom. Okay, so as a result, okay, the surrounding hot air, okay, actually replaces it. Okay, so this allows us to form a very nice convection current over here to cool the room. Okay, but if you put the aircon at the bottom, okay, so what's going to happen now? Okay, your cold air will continue to sink. Okay, while your hot air will continue to stay on top. Okay, this means that the heat is not really exchanged, okay, and it's not very effective in cooling via conduction. Okay, there's another type of common convection current question. Okay, and they actually ask you, okay, how will the convection current look like? Okay, so remember that, okay, the hot water always rises. Okay, so since the heat is here, okay, the water over here will be the hottest. Okay, so the hot water over here will actually rise. Okay, while the colder water will sink from the side. Okay, but if you look at this over here, okay, now the heat is on the left hand side, which means this part of the water is heated first. So how will the convection current look like? Okay, the hot water over here will rise. Okay, while the cold water over here will sink. Okay, it's quite similar for the third one. Okay, but this time right is on the right. Okay, hot water will rise and cold water will sink. Okay, so you realize that it actually affects, okay, how my convection current will look like. Okay, after convection, okay, we also have our radiation. Okay, transfer via radiation. Okay, so what you need to know is, first thing, it does not require a medium. Okay, and second, okay, what are the factors affecting the rate of energy transfer? Okay, so there are three main things, okay, affecting your radiation. Okay, the color and texture. Okay, so for color, okay, normally we have black and white. Okay, black, okay, has a high rate of transfer, which means it's a good absorber and emitter of thermal radiation. Okay, while white is a poor absorber and emitter of thermal radiation. Okay, dull is a good absorber and emitter of thermal radiation, while shiny have a low rate. Okay, for surface temperature, okay, a hot surface or high temperature surface have a high rate of transfer. Okay, while a cold surface have a very low rate of transfer. Okay, lastly, okay, surface area. A large surface area, okay, have more area. That's why they can emit more radiation, okay, as compared to a small surface area. Okay, you also need to know, okay, the applications, okay, of the three main mode of transfer. Okay, so one common example, okay, will be, for example, this is the wall of a thermal flask. Okay, and inside is actually vacuum. So they will ask you, oh, why is it vacuum? Okay, now we know that because conduction, okay, requires a medium. Okay, by having a vacuum, it actually reduces the rate of conduction. Okay, so an object that's inside it will actually heat up, okay, or cool down slower. Okay, another type of question that they will ask you, okay, to actually identify the main mode of transfer. Okay, so when I say main mode, okay, it means that, okay, which mode, okay, conduction, convection, or radiation, okay, transfer the heat the fastest for that context. Okay, so what are some questions we can ask ourselves to identify it? Okay, first thing we need to know that typically conduction is the fastest, followed by convection, okay, then radiation. Okay, so for conduction, we ask ourselves, okay, are they in contact? Okay, if they are not in contact, okay, then we ask ourselves, okay, is the medium a metal, non-metal of gas? Okay, if it's a metal, then okay, conduction is still the fastest. Okay, but if it's a gas, then conduction will probably not be very fast. So we'll look on to the next one, which is convection. Okay, for convection, we need to identify whether the object is directly above or not. If directly above, then okay, convection will be effective. Okay, if not, convection might be a bit slow. Okay, so the main mode of transfer in this case will be radiation. Okay, so take a look at this example over here. Okay, I have a marshmallow at this side, okay, of the fire. Okay, it's not touching. Okay, and in between is actually air. Okay, since air is a poor conductor, okay, conduction is probably not the main mode of transfer. Okay, next we look at convection. Okay, because it's at the side, okay, all the hot air actually rises, okay, and don't travel towards the marshmallow. Okay, so convection is not the main mode of transfer over here. Okay, as such, okay, radiation, okay, is the main mode of transfer. Okay, and with that, we actually come to the end of this summary of the transfer of thermal energy.